All right, so welcome everyone again. Today's session is an introduction to ARM and statistics. We're going to really be totally just within PowerPoint here, talking about the statistics, at least ones we encounter within ARM as it relates to agriculture research, and really set the stage for the future webinars that we'll be giving on how to actually do it in the software. So we'll get a nice overview today. And so let's get started here. If I can get my presentation to move, here we go. All right. So the goal of research is typically you're determining whether treatments of interest are performing differently. Of course, your choice of treatments, they could be different products, different formulation, different rates of application. Whatever they are, we want to know if those treatments can be distinguished from one another in their effectiveness, in their safety to the crop, or their cost. Sometimes maybe the hope is the performance is indistinguishable if your product is cheaper. But research trials are then performed to obtain observations of that treatment performance. In the ARM world, at least, we usually call them assessments or ratings. But the question is, are the observed differences due to the treatments or just due to random chance? And that's where statistics comes in, namely the analysis of variance we'll be talking about today. But you should not just immediately jump into the analysis as soon as you have data that you've recorded. I call this middle step data confirmation. And that's important to catch outliers and any issues with the assessment before we go to the analysis. And the reason being, an outlier really breaks all three assumptions of AOV, which we'll kind of dive into later. So we'll get into the specifics of that later, but really all of those issues that we're going to be concerned about and looking at, if we have an outlier in the data, that's going to mess up all three of those, which is very not good. So we want to kind of catch those as soon as we can, even before we're later on in the process. So how should we avoid these types of problems? If you keep detailed records of the site and the assessment, and confirming the data as soon as it's taken are really the big methods for doing that. Those both happen to be kind of our fundamental benefits of the data collection options that GDM offers, the tablet data collector and the ARM mobile. And you can also identify the like an acceptable range of values that you would expect from that assessment before actually taking the assessment. Would be another way to kind of get those parameters set and make sure that the data that is recorded is accurate. And so this topic here is really going to be our day 2 of our series next week, the data confirmation. And we'll look at the different tools within ARM that we can use for this step. So once we've confirmed the data, now we can kind of think about the analysis. So agriculture research is always subject to variation from a variety of sources, and so we perform an analysis of variance on the data. Statistical variance is a measure of how spread out the data is about its mean. This is also called ANOVA or AOV, but the analysis of variance dissects the variability in your recorded assessments. So you have controlled variability from the treatments and the blocking structure, if you used one, and then you have the experimental error, which is uncontrolled. Then basically, we're considering if the observed difference if the observed differences are due to chance, then the variance between the treatments would agree with the variance within treatments. is really kind of the whole theory of what we're looking at in this analysis. So to give an example that we can kind of chew on and talk through, here is an example output of the AOV analysis, just from a kind of a random trial here with 5 treatments and 4 replicates. We'll just kind of talk through each of these components here and how they're calculated. The first, I guess, would be the second column there, the degrees of freedom. A little hard to define, but it's the number of values in a final calculation that are free to vary. So if we're looking at variance, here's what we're analyzing. The degrees of freedom equals n minus 1. So for treatments, if we have 5 treatments here, then we have 4 degrees of freedom in the treatments there, that second row. And really that one that you're taking away is kind of the mean is calculated in order to determine the variance, kind of how you end up with the n minus 1. Next column there is the sum of squares. So that represents the amount of variation in the data. And of course, now we're splitting that up into each source here in the table. And in our case, it's between the blocking, the treatments, and the unexplained, the error. Next is the mean square. So that is the sum of squares divided by the degrees of freedom. So really, we're taking the amount of variation and divide it by the degree to which it can occur. So next, then we can calculate an F ratio. And so that's indicating the level of variation from that source compared to the random variation. So the larger that ratio is, the more likely the variance from that source is not due to just random chance. So kind of quantify that largeness or lack thereof, we calculate a p-value. And that's the probability that the observed differences in the treatment or the block means could have arisen by chance. So a low p-value, typically we set the cutoff at 5%, indicates that we can be confident that there are real differences among treatments. Whereas a high p-value, like we have here between the blocks, indicates there is no evidence of a real difference, in this case, within the blocking. So this could be because there's no real difference, or the differences was just too small to detect. All right, so long story short, to summarize, the AOV analysis is breaking apart the variance of our observations into different sources. Then we calculate a p-value as the end result. And that p-value is a probability, is important to remember there. So the AOV p-value is the probability that no differences in treatments exist. So that p-value of 0.04 we had in our example means we are 96% confident that there are significant differences between the treatments. However, we're not done yet. Now we need to know which observed differences between those treatments are significant and which are not. So the AOV analysis doesn't provide an answer about which of those differences are significant, just whether there is evidence that some difference exists. So our next step is to run a mean comparison test. Also, they can be known as a multiple comparison test or a mean separation test. These compare your treatment means to determine what differences are significant. So we've got a variety of options of different mean comparison tests within ARM. kind of varies on the different situations, your different types of research, which one you may want to use. Kind of the most common ones here I've got on the screen, the LSD, Duncan's, the student Newman-Kuhl's, and the Tukey's HSD are the more common ones. We have a few other ones in the list as well, but those are kind of the headliners, if you will. Kind of a common question then is, well, which one do I pick? What one should I be running? And there's a couple of things to consider. First one, not necessarily getting into any political discussion, but your tests can be classified by how liberal or conservative they are. And really that, whether they are more likely to report a false positive, triggering the type 1 error, or a false negative, the type 2 error. And so you really want to consider the penalty of failure for the particular study. So if you're using, a trial that's being used for registration, you would really want to choose a more conservative test. But for like a screening trial, it's all about potential. So really now a more liberal test would make more sense. We're not really worried about a false positive at that point. We're just trying to find any potential that we can, and later down the road in further experiments we can narrow things down. So that's one good way to look at that. We do have a handout that's out on our website. I'll also include it in the email for with the recording. But kind of gives an overview of statistics, kind of some of the stuff we've been talking about today. Page 2 of that handout has more of a breakdown of each of those main comparison tests, so we don't get too bogged down in the individual ones there, but that can be a good resource if you want to know more about each of those tests and some examples of when you use it. You kind of talked about the overall look here, but of course, a lot of times it depends on just the type of research. Well, in my industry and in this type of study, most people use this, and a lot of times that kind of trumps some of the other choices. You just picking the one that everyone else does can be a good choice as well if that's where you're submitting the information to, might have that requirement. So. All right, so maybe just to walk through an example of how a mean comparison tests work. Each one's a little different in how it calculates or does things, but I think the basic concepts are the same. So we'll just kind of work through one example here. And the first step typically is a test statistic is calculated to perform the actual comparison of the means. So we're going to take kind of just the easiest, computationally the easiest of the mean comparison test, the LSD. And so in our case, the LSD test statistic ends up being 5.49 for this data. Then we compare the individual means using that statistic. So if the two treatments do not differ by at least that LSD amount, then they are not considered significantly different. Then letters are assigned such that means with no letter in common are significantly different according to the test. So looking here, we can say that there is evidence that treatments 2 and treatment 5 are different because there is no letter in common. But there is no evidence of a difference between treatments 4 and 5 because they have that letter A in common. Quick kind of aside on the LSD test here that we talked about. This particular test is intended only for specific comparisons chosen before the data is collected. was really the design of that mean comparison. When you use this to make more than one comparison, like across a whole trial we did in this example, the true significance level becomes much larger as the number of treatments increase, because really you're making a lot more pairwise comparisons. So for example, starting out in this design, in this study, we were most interested in treatment 2 and treatment 4. And that's really our main comparison that we wanted to do to make sure that our product, treatment number 2, is better than the standard in the area or whatever. And so that was the main comparison we wanted to perform. And that's great to run that LSD, use that 5.49 to decide if we have significance or not. But when you do that across all 5 of these treatments, now it's not just that one comparison of 2 versus 4. It's now 1 versus 2, 1 versus 3, 1 versus 4, 1 versus 5, 2 versus 3, 2, and so on. And so especially you can imagine how more treatments that are added now, there's so many more comparisons being done. And this LSD is just so liberal that you just have to realize it's very much likely to end up with false positives, essentially. So just kind of a word of warning. It's one of those popular ones. It's very simple to look at. In fact, we have that statistic, the LSD statistic, just you can turn on an AOV report, so you can just eyeball a particular comparison. And it's handy for that, but just to kind of point out the potential downside as well for that particular test, at least. So great for a single comparison, but setting that as your mean comparison test, hopefully at least just do that being aware of the ramification, that it's very, very liberal. You're most definitely going to get some false positives there, which may be just fine, like we said, depending on the experiment. But all right. So moving on, kind of one big caveat to all of this analysis we just talked through, and we kind of mentioned this earlier, is that ANOVA has some requirements of the data that it is being run on. And so if these requirements are not met, then the results of the AOV analysis really can't be trusted. We can't rely on those if we didn't meet those requirements. And so we call these typically the assumptions of AOV. So the first assumption is homogeneity of variance, that the variances within treatments are approximately equal. If you have a treatment that is much more variable or much less variable than the others, then the ANOVA will not work. So to determine if this is the case, we can look at a box whisker graph and run a test for the homogeneity of variance. Levine's is generally chosen, but we also have Bartlett's as well. Just statistical tests that can give us, again, a p-value to tell us yes or no, is there the likelihood that we have an issue with that assumption or not. The next requirement is that the data is normally distributed or approximately normally distributed. If your data is not bell-shaped, then you can't use the same p-values in the analysis. As Peter, our statistician, would say, it's just math. So tests for this include skewness, kurtosis, and Shapiro-Wilks. And all of these are in ARM, and we'll see them later on. Finally, the last 2 assumptions are independence of errors and additivity of treatment and block effects. These are harder to test, but generally are not an issue. Really, the biggest thing here is to just not introduce bias in the assessment. Things like edge effects or subjective ratings being influenced, things like that. I think are typically kind of at the forefront of a researcher's mind anyway when setting up an experiment or taking that rating. as far as just taking a look at those types of things, the assessment map, that's kind of a heat map of your data put onto a trial map, that can be useful to detect some of those things. Again, typically we don't spend tons of time on those, just from a testing standpoint here in the data review. So this section right here really will be then our third session in this series, a couple of weeks from today, on the data review. So, looking at, the box whisker, we kind of will see in data confirmation, but that could play a role here. And most of their time will be on the column diagnostics tool for that data review session. So what happens if we do not meet those assumptions? There are data correction transformations, which are designed to correct the underlying distribution of the data without affecting the results. So there's kind of the three main ones that are used and available in ARM. The logarithm really is great for counts of things that occur in clusters. So the kind of the underlying distribution would be a log normal distribution that you see for things like that. And so that log transform can take that data and get it into the right distribution for us, essentially. The next one is the square root transformation. That's really for counts of things that occur at random or rarely. So you might have a lot of zeros in your assessment and then an occasional 2 or 5 or 3. Very, very hard to make that look bell-shaped, as you can imagine, if you have so many of things not there. And so that follows a Poisson distribution. And the square root can kind of get things back closer to the bell shape. And then the last one is the arcsine square root percent transformation. And those are great for percentage assessments that tend to be a binomial distribution. So really the idea there, we're going to perform a transformation on every data point. So we're going to treat them all fairly by performing the same calculation on each data point. So that way the results that we have of what's the same and what's different should still, in theory, remain the same. We're just transforming all of those values. So that way then our resulting values can kind of fit those assumptions. Is really the concept behind these options and why we would do them. Another option for us is spatial models. And those really try to recover information about hidden variables across the field. In ARM, we have 3 different trend and 4 nearest neighbor models that can be used. These are typically only used when your blocking design fails. And we'll kind of talk about that a little bit in the data review session. Kind of more of a last ditch effort that you would do. I typically don't recommend people just immediately jumping to the spatial models when one of those assumption tests fail, but kind of a let's try everything else that we can and see if it'll work. And then, okay, nothing's working, or we looked at our data and found that our blocking failed. It's something, we had a totally different gradient than what we were thinking, or whatever. And you kind of have to throw out that blocking structure that was tried. Well, now let's pivot. What can we do since everything's already said and done? Then let's bring the spatial model and try that out. So it's kind of a when all else fails option. But we do have these models in ARM for when they may become necessary. Finally, third option for us would be to use non-parametric statistics. And so that actually just throws out AOV and its assumptions. And instead, we're analyzing the data by ranking the assessment values. So we're, instead of dealing with means and standard deviations and things like that, we're totally just not doing that process. And instead, we're going to just look at the data values and assign ranks to them. This is the highest value, the second highest, third highest, or vice versa. I don't remember if we start high or low, but either way, you kind of rank the values. And now that's what you can manipulate and look at is the ranking of them. The nice thing with that is that you can still run a mean comparison test. You just simply would use the mean of those ranks. So we can still then compare the different treatments in kind of that same fashion that we've been talking about, but it's just not using the AOV, but instead the non-parametric statistics. A question here about ARM allowing you to calculate ANOVA and the statistical significance even when the assumptions are not met. So that is true. So ARM can provide warnings and alerts to say, hey, the assumptions of AOV are not being met, but at the end of the day, it's not going to stop and prevent someone from generating an analysis. So I guess it doesn't mean for 100% certainty that the results that you would see on that report are totally wrong. But it would give me some concern, I guess is what I would say. From a statistical standpoint, the confidence that that report is telling you the whole story, I think would be compromised. It's with statistics, it's very rarely black or white. That's wrong. That's right. But yeah, if you skip this data review process or do not take any actions and just proceed with the analysis, even though there may be some issues with the assumptions, yeah, ARM, the software is going to say, okay, I'll do it for you because that's my job. Here you go. And it certainly could be fine. You could make the right decisions from that, but you're kind of playing with fire, I guess I would say, because there's the chance that the analysis isn't totally right. So yeah, like I said, kind of hard. Statistics very rarely is black and white. So that would be a case where no, it's not like everything on that report's wrong and everything you've looked at is wrong forever and ever, but certainly you could improve the effectiveness of the analysis definitely by taking into account these assumptions and making use of these tools to put things right and to set yourself up, set that ANOVA up to be the best it can. Would maybe be the best way to approach that question. But definitely a great question. That's kind of the fun, I think, with statistics in general. Is it's always a gradient. It's always kind of trying to find the sweet spot. There's never a definite right or definite wrong answers. So really great question. And as that happens to be here, this is my last slide. So like I said, kind of giving an overview here to set the stage for our next sessions, which here I can bring back on the screen. That we've kind of talked about them a little bit. We'll do the data confirmation next week to talk through that. Okay, my data's in, and now let's make sure that it's what we want. Then data review will be the big talking through the assumptions of AOV and how to set things right. And then we'll look into the reporting and all of the options in ARM to get that right. Question here, among the post hoc tests you listed, which one is the most conservative or liberal? So let me go back here to that slide. We had these four here that I mentioned. The most liberal was the LSD. So that one's most likely to give that type 1 error. The most conservative is the Tukey's HSD. So that one is most conservative. So, much less likely to give you the false positive, but then on that flip side, now you have that type 2 error chance of missing a significant difference and having a false negative. And the order in ARM, so if you're in the ARM print reports and you're looking at your AOV means table options, it's about the very first option on that page, your mean comparison test. If you bring that drop down, the list of options there are in order of most liberal to most conservative. So I believe LSD would be the first one you would see in that list. I think Duncan's is next, and then SNK. I could be wrong. They're both in the middle, and then Tukey's would be the fourth one there. So yeah, Duncan's is a good compromise between the two. Same with the student Newman-Kuehls or the SNK. They are both kind of in the middle there, less extreme. So a nice balance. I think our default in ARM is SNK, which yeah, I think it's on the conservative side of being in the middle. And Duncan's would be on the liberal side of the middle. So a little more reasonable, less extreme than the LSD. A little more reasonable, but on the liberal side. So yeah, definitely those middle two are a nice compromise to balance those two out. So a great question. And like I said, those four are kind of the big four. But then after that, in the list in ARM, there's a couple other ones that are a little less common, but have some nice specific use cases in particular industries, types of research. So they are there for that purpose. But these are kind of the general big four, if you will. Great questions. Any other questions? So for a variety trial, is Tukey's too conservative? I'll admit I don't have research experience, so I would be going based on hearsay. For something like that, I would say kind of two things to consider when choosing that or making that determination. Is Tukey's too conservative for me? Number one is, do I see that a lot in the variety trials that are done in my area or in my industry? Is that typically how people are reporting it? Do people use Tukey's a lot? And then the other thing to consider is maybe at what stage in this variety testing are we at? If this is really early on, we're just kind of trying to see what could take off, then I would say, yeah, maybe avoid Tukey's because it's so conservative. And if you're screening, you really want that potential. But if you're kind of really trying to nail down something where we're looking at registering, or we need to be really confident that the differences we see are definitely there, then Tukey's would make a lot of sense because you want to be sure you don't want any false positives. So that's typically the biggest question, at least that I ask, or I have people ask themselves, is really that question of how important is it. And that was kind of on that next slide, I guess, to recap those options, the liberal versus conservative, but also the penalty of failure. Originally ARM and way back in its early days was really only for crop protection. And then that was a really, really important penalty of failure. If it doesn't work, what happens? And you really would impact your yield or whatever your end result that you're hoping for. So really, really important to make sure that those results are true. Nowadays, there's a lot more biologicals out there, and so that's a totally different ballgame with the penalty of failure. So there's definitely a wider range, I think, nowadays of options and what gets used because of that range of the penalty of failure. So. Great questions. All right, well, we finished early. This is probably about the only session that I ever do that we we get done early. I talk a lot, but we'll have time. Hopefully, you'll all be able to join us in the coming weeks to dive into ARM. We will stay out of the slides for the rest of the sessions, and we'll be in the software the next 3 weeks, same time, same place, to kind of walk through these. So thank you all for joining us today. And hopefully we'll be seeing you soon at these future sessions.